Are we recording? Yes.
Here we go. Hello, welcome everyone to the FORTH 2020 Zoom meeting in May 2022. Here we have an exciting schedule today. And our first speaker, I'm happy to introduce you, Brad Rodriguez, and he will talk about breaking the 64K limit. And today it doesn't seem to be a big issue with all the memory lying around, but he has something very interesting to tell us. So Brad, are you prepared to go ahead?
I am prepared to go ahead, and I'm going to do that trick from last month of shutting off my video feed now and then sharing my screen. So if you want to see what I look like, this is your chance. Stop video. Share screen. Okay.
That looks fine.
All right, splendid. Breaking the 64K limit. As you noted, this is sort of an older notion. This is going to be an issue on handling extended memory in Forth, but it's a historical overview because the 64K limit is ancient history at this. Well, it's not really ancient history. We'll get to that. I was going to say, in days of old, when knights were bold. No, that's not it. Wrong rhyme. When olden ships had 16 bits and 64K ceilings, these odd designs gave address lines, and some are still appealing. That little composition explains what we're about here, that when you are dealing with a 16-bit address limit, either a 16-bit processor limit or just a 16-bit Forth model, what happens when your program requirements or your data requirements, but mostly your program requirements, exceed the 64K space? And I've, over the years, solved this problem a number of ways, and I will share with you 5 of them today. But as Ulrich has already hinted, I want to start off with first the obvious solution: use a 32-bit CPU. This isn't 1980 anymore. 32-bit CPUs are cheap and plentiful. I think you can get an ARM processor for a few dollars. I know I can buy an ARM processor on a board for $12. So that's generally the engineering solution, is to, if you can, just pick a CPU that has a larger address space. All of the schemes I'm going to describe today violate the AlexForth standard. They are not going to be standard Forth systems. The AlexForth standard, first of all, it assumes a single linear address space. It doesn't have multiple address spaces, and it's not bank switched. And it also assumes that the address size is smaller than or equal to the cell size. If you have a 16-bit cell size, then you can't have an address size larger than 16 bits. An address has to fit in a cell to be ANS compatible. But if you're willing to discard ANS compatibility, you can have some fun. Okay, the first and most, probably I should say the first and easiest approach is a split instruction and data memory. And this goes back at least to the PDP-11, probably much farther than that. In the microcontroller world, I've done this with a Z8 microcontroller. You can actually do this with an 8051 as well. And that's that the processor distinguishes between instruction fetches and stores and data fetches and stores. And so you have a 64K instruction space and a 64K data space. The Forth modifications required for this are similar to those of a RAM and ROM system. If you do embedded work, you're used to the idea of variable having to change its definition. Instead of variable returning just the next address after the code field and returning the parameter field address, variable has to have a pointer to a location in RAM somewhere. Similarly, for split instruction and data memory, you need new operators like ifetch and istore to fetch and store from instruction memory. Some people call it code memory, but cfetch and cstore already have meanings in Forth. So I use instruction memory and I say ifetch and istore. There's an IDP, a separate dictionary pointer for the instruction space, and so on. And if you want to see this in action, most of these modifications are in the MSP 430 Camelforth, though those are not a separate instruction and data space enforced by the processor. Those are just the RAM and ROM modifications. And again, once you do this, you've broken ANS compatibility. ANSI assumes that you can look at the parameter field of a word with fetch and store, and you don't have to use ifetch and istore. Taking this to the next logical step, you can have more than two 64K segments. You can use segmented memory. And those fine folks at Intel introduced us to this way back with the 8086, where it had 4 64K segments of addressing. Turns out there's actually 5 separable areas in the Forth model. There can be code, which is the machine code, data, stacks can be separated from data if necessary, threads, which are the high-level code. This is the threads are what the inner interpreter is traversing, those strings of addresses, and headers, the dictionary, which actually has the names of the words and the information about them. Those 5 areas can be separated, and in the Camelforth 8086 model, we have code and threads together in the code segment, data in the data segment, headers in the extra segment, and then stacks in the stack segment. And allowing 32K for stacks is probably a bit excessive, but that's what I drew on the diagram there. Having separate stacks and data brings some interesting ramifications, because a lot of people are used to being able to address inside the stack by doing SP fetch, modifying that address, and then doing a fetch. When you have a segmented memory system like this, that is no longer possible. This can break some local variable schemes that expect to store variables in the stack somewhere. So just be aware of that. And again, there's an example of this in Camelforth for the 8086. It's possible to simulate segments if your processor has high address bit support, and you can get other interesting notions there. So my third approach is a segmented model with a long interpreter pointer, a long IP. The example that I have done is for the Freescale 56800E series, which had 24-bit address registers. This, I think, also is a good match for the MSP 430X, which has 20-bit address registers, but I haven't implemented that one yet. And in this, you simulate segments by using the high address bits. When you're doing a data fetch with fetch and store in this illustration, it would stuff the value 5 into the high 24 bits. If you're doing a header fetch, it would stuff the value 4 into the high 8 bits, the high part of the address. High 8 bits or high 4 bits, depending on the processor. And the thread space is shown here as being bigger than 64K because we're allowing the interpreter pointer to be bigger than 16 bits. All execution tokens, and this is standards friendly, all execution tokens are in the 64K code space. So execution tokens are all 16-bit. And if you have a high-level word, high-level Forth definition, what you have in code space is a code field and then the address of a thread in the thread space. The 32-bit, well, twice 16-bit, the 2-cell address of a thread in the thread space, and then the interpreter can go through that. This does require that return addresses, Forth return addresses as pushed on the return stack, not the machine return addresses. This requires that the interpreter's return address is 2 cells. And it turns out, as far as I know, that's ANS compatible. There is no ANSI specification for how big a return address can be. However, an awful lot of people, myself included, have been known to use constructs like R from drop to get rid of a return address and to bypass one level on the return sequence, return stack. And R from drop doesn't work anymore. It has to be R from to drop. So be aware of that when designing your applications. But other than that, this is probably one of the more standards-friendly modifications of the ones I'm discussing. Now I need to talk about conventional paging, the way it's been historically done. And I'm going to use an example of a processor with external memory. This is vastly oversimplified, but assume that you have a microprocessing unit and you have you have a small ROM, a small RAM, a big ROM, and a big RAM, and you want to access all of the big ROM and the big RAM. As I have shown here, the address space of the microprocessor is divided into regions. One of them addresses the small ROM, one of them addresses the small RAM. The other two address the large ROM and the large RAM, but that is with the addition of some extra address bits, which are shown here as X0 to X3, and might come from an output port. So in this case, you would write, if you wanted to access a location in the large ROM, the large RAM, you would write 4 bits to X0 to X3 and then address in the in the paged address spaces. You have to have common RAM and common ROM. One thing, if you want to do any operations that fetch or change the page register there, the page bits, that function has to be in the common RAM so that you can't change the address to a whole different block of ROM while you're in the middle of executing a routine. Interrupt vectors also need to be in the common ROM, and at the very least, stacks have to be in the common RAM. So when I refer to the common ROM and the common RAM, I refer to areas that can always be accessed regardless of the setting of the page register or the page bits. Now, this can be done with pretty much any microprocessing unit that has an I/O port, but some microprocessors actually have built-in support for that. The MC9S12 has 3 registers for paging. It's the P page, program page, R page is RAM page, and E page is a page register for the E squared ROM, E squared PROM on the chip, so not that useful for us. And because I know we have some 6502 presentations today, I had to do a shout out to the 65CH16, which is an improved version of the 6502 that in fact did what they referred to as bank addressing with a data bank register and a program bank register. So if the processor has processor level support for paging, there will be additional address pins available on the chip. Otherwise, you can use an I/O port. For implementation, we have to have an interpage call, what I'm referring to as the long call, and an interpage return. So when you want to call if you are in the paged area and you want to call a routine or word in a different paged area, what you have is this construct that appears in the thread. You have first the address of lcall, which is a 4th primitive in this system. And lcall expects to find a page, which is 8 bits, and a word address, which is 16 bits. Now this requires a modification of the compiler. The compiler has to be smart enough to know what page it is currently in and what page it is trying to call a new word. If the page it is in is different from the page it's trying to call, it has to build this lcall, 5-byte lcall. If the compiler sees that you're calling a word in the common ROM, or you're calling a word in the same page, then you don't have to use an lcall, just a regular 16-bit address in the thread is all that you need, because the page register does not have to be changed. Data access, we need the long address operators. So I think traditionally these have been lfetch and lstore that take a 2-cell address on the stack. So lfetch takes a 2-cell address and returns the value it finds at that address. Again, these routines should be in common ROM because you're changing the page register. And LStore similarly takes a 16-bit value, or a 1-cell value, excuse me, and a 2-cell address and stores. Also, we have the problem of execute. Execute is broken by this because execute takes only a 16-bit, well, single-cell address. You need an L execute to take a long address and do the call to a different page, or to an arbitrary page, I should say. So I've implemented that on the 9S12, and I have not implemented it on the 65CA16, but someday perhaps I'll get my hands on an Apple II GS that use that chip and give that a try. Now, for another project, I did a variation on this, which I refer to as page prefixes. And this specific example used the H8S microcontroller. And this is the idea that you put a prefix word in front of a word address. The prefix word specifies the page. So in this specific example, I use 0180, 0182, 0184, and so on to specify pages 01, 2, 3, and so on. But that prefix word actually is a fourth word. At 0180, there is a fourth word that gets executed by the inner interpreter. At 0182, there is a fourth word that gets executed by the inner interpreter, and so on. And the function of those prefix words is take that page number and append it to the word address that follows, and then do that, perform that word. And that actually is on the side there, the H8 code, the H8S code to handle this. It's a direct threaded model. So at 0180, there is a code field, which is actual code, and it's just a relative jump to do prefix. At 0182 is a relative jump to do prefix. At 0184 is a relative jump to do prefix. And do prefix takes advantage of the fact that the W register will have the contents of the, have the address of the prefix word. So the W register will have the value 018N, whichever one you use. This has the advantage that it gives you 64K pages. If you're doing anything in the first 64K in page 0, you don't need a prefix word. So your fourth kernel is in that page, and you've got quite a lot of words that you can access without any addressing. And it's a simpler modification to the compiler. The distinction between this and the previous method I was talking about is this compiles a long call anytime you're calling outside of page 0, even if you're already outside of page 0. It's not looking for a page to change. It's just looking for, is the page of the word 0 or some other value. So I have done this on the H8. I think this is probably the other model I might try implementing on the MSP 430. So there, with a real whirlwind presentation, are 5 models for extended memory addressing. Applications. Well, I think the 56800E and the H8S are now purely historical interest. They're still manufactured as far as I know, but I think if you go look for those on the manufacturer's website, they'll say that wonderful phrase, not recommended for new designs. The MSP 430 X, the extended addressing model, the MSP 430, the 9S12 are still current processors in current production being used in new designs. And again, because we got some 6502 people here today, the 6502 and 65H16 are still being used for historical reasons, that if you want to keep an old board running, or you develop a new board using an old processor. So this might be of interest to those of you doing historical processors. And with that, I will throw the floor open here for questions. There we go, questions.
I have one. Of course, it's related to 6502. Well, actually, if I wanted to convert my code from 6502 for the fourth code and wanted to go to the 65816, not in emulation mode, I mean, there's going to be a lot of changes because of the addressing space, long branches, long jumps, and whatnot. Does that mean a complete rewrite of the code, that there's some fourth out there that exists that would fit the bill with that processor?
Okay, I need to confess that everything I know about the 65H16, I learned from the Wikipedia page. I've never used one. I would think that, yes, you're going to have to rewrite pretty much the whole kernel to make use of the 65H16's expanded addressing mode and expanded capabilities. 16-bit X and Y registers, and you have a 16-bit accumulator. So yeah, I think you'd want to, yeah, you could run a 6502 fourth on an H16 in emulation mode, but what's the point? What you want to do is use the expanded capabilities of the H16. So yeah, I'm afraid you're going to be rewriting a lot.
Yeah.
Hang on a second. Any other questions? I see something here in the chat bar.
Yeah, Alexandre. 65CO2 isn't just still here for historical reasons. There's active research and development in 6502 space today, like 6502 silicon on plastic, flexible 6502. The 6502 is still produced and will probably keep to be relevant in the future. So more a remark than a question, I think.
Ulrich, is that because the transistor count is so low? So is the transistor count low on the 6502 design, and therefore it's a good processor target when you've got low density technologies?
Yes, it is.
I believe the Z8, which is a really old microcontroller, the Z8 is still manufactured as well, and they do several variations for specific applications, several variants. But yeah, a lot of these old microcontrollers are still available. And yes, when you start talking about making the model available so you can do custom silicon, a lot of them are available that way.
So, are there any additional questions to Brad?
I'd just like to add a comment, really.
Yes.
Some years ago, Brad, I implemented a 17-bit forth on the MSP 430, the F5529, I think it was. The problem with it was that you can only access the bottom 64K normally, and the amount of I/O space, because it had so many bits and pieces on it, it got down to something like 48K, I think, of usable program space. And I discovered that since all instructions must be aligned to an even address, I could use the bit 0, the odd bit, to indicate the top bit. So and this works. So they gave me 128K space. But with hindsight, it was a huge effort to do. It's not that complicated once you got it to work, but it is complicated. And as you pointed out, you've got to adjust the compiler to be aware of what it should be doing. But it's an absolute nightmare from the point of view that if I want to hand this program on to anyone else, I've got to give them my modified version of the compiler. So anyway, but it's great fun doing these kind of things.
Yeah.
Oh yes.
Yeah.
I like that. I've never even thought about that approach. That's great.
What was really good is that you lose the speed because you've got to use the extended instructions, and there was a 20% speed reduction, but a almost factor of 2 increase in the available program space, which I thought was worthwhile.
Yeah. So thinking of DOS, where you also had this limitation, there was this famous FPC system by Tom Zimmer that did segmented threaded code. So it also had 2 items on the return stack for storing the return addresses. And this worked fine. So that was the pre-successor of the Win32 force. And lots of people used it at that time. And yeah, great.
Yeah.
Additional questions, comments?
Yeah, can just
Peter.
Hey, Brad, I just talking about this extending the 16-bit address range. I do this on 32-bit processors. I've got the P2 8-core processor, but my fourth uses 16-bit address tokens. It's nice and compact. I don't want to go to 32 bits, but all I do is I just have a paging instruction codes, one instruction code for for, you know, the next page up to 64K, you know, page 1, page 2, etc. And it only flips that page for that call. Any other call is normally back to the kernel. So I find that 16-bit is also an address token. So a certain range are decoded into literals and branches, etc. And I, you know, like, why would I waste 32 bits? 16 bits, just perfect. And practically everything fits into 64K as it is.
Mm-hmm.
You know, even on 32 bits, I'm saying we still do it. But I don't have a problem with the return stack.
Yeah.
That's actually quite a good argument for using a 16-bit address model on a 32-bit MCU, because it would be smaller. So thank you for that. That's a good point.
I think so. All right. Other comments? Well, then, Brad, thank you very much.
Thank you.
Very enlightening talk, and yeah, lots of thoughts of things to implement on microcontrollers, and even the modern ones, as we just found out. Thank you very much. So we proceed with Chang Luke, and he will talk about a disassembler generated by the assembler in an automatic way. I'm very curious what this actually is. So
Ulrich, I think he did not arrive to the meeting, so
okay.
we let this interesting talk for next
so
time.
we need to be very curious and hold this up, and so yeah, well, then we skip him. I'm sorry that I didn't check the participants. So Vladimir is with us, I guess.
Hello.
Rob, sorry. I changed the meeting. If you read the schedule, because Rob Probin just arrived from USA from a trip, and he's very tired. So Vladimir, can you allow us to shift you one?
Well, okay.
And we present Rob, and after Rob, you are
okay.
next.
Okay.
Okay.
Yeah, please. Yes.
We just
sorry for that.
Rob in. Yeah. Okay. Now I updated the schedule on my side, and I see the revised schedule. So I loaded it up front, and then I didn't get that. So sorry, Vladimir. You will be next then. But Rob, he will talk about FORTH and Bluetooth Low Energy.
Yeah.
And
can you guys see my screen?
We see the slides very well.
Okay. So yeah, I've got the first few slides are just talking about wireless for mobile robots generally. I've tried to keep it short and simple. Then I go into some Bluetooth low energy stuff. So I'm sure a few of you know this, but often people have done bits of this, and especially if you're dealing with 4 systems that aren't bolted to a wall or just on the table, how you access, it's quite often very useful to access the fourth prompt when the thing's moving. Obviously, for fully autonomous systems, you can't necessarily. It's difficult to remote control over FORTH, but I still found it quite useful. So let me just walk through. So obviously the first thing that you shouldn't discount is a wire, right? You can get maybe they used to call it mod wire, or you can get a piece of just 3 pieces of ribbon cable on a long stretch and suspend it. Obviously, it depends on how mobile the robot is and how many turns it makes. But sometimes the simple is, don't let the perfect get in the way of the simple. Sometimes this, and I found a picture from somebody else who was doing this on a FORTH system, but they were tethering a fiber optic cable, which I thought was maybe more than I've done. If you've got a robot that's only got limited movement, that's sometimes it's just a good option. Either you can just go ground and RX if you just log in, or Although sometimes you can log that to local memory, maybe an SD card or something. But if you want some sort of control, then you just need 3 wires. The second one, probably that several of you have come across, is Wi-Fi. So on some of my robots that have got Raspberry Pis on, Wi-Fi is a very good solution, especially I found, I mean, it's possible to set up the Raspberry Pi either with a dongle or with the wireless chip to use Bluetooth or Bluetooth Low Energy. It's usually not worth the effort, right? If you've already got Wi-Fi on your board, it's well worth seeing what you can do with Wi-Fi, because on a board like the Raspberry Pi where you've got Linux, you can just SSH in and run Forth on one terminal, and then you have another terminal with some display stuff. You can open multiple sessions with 0 effort. Obviously, there's quite a lot of fans of the ESP32 on the group, and that's that. And its slightly older cousin, the 8266, sort of causing a bit of an explosion. I've got, I guess my camera's still on. You can get modules like this. You can actually get for this in 8266 on a prototype board. You can actually just get the module bits and solder that on, and it's you know, the ESP03, which is an 8266 board, is 12 millimeters by 17 millimeters. There is some disadvantages in terms of cost and size and power, and complexity as well. So if you're just controlling something over a SSH session to Raspberry Pi, it's easy. Sometimes it's not right though, and you really want something somewhat simpler than this. So the next easy solution is this, which I'm sure you've seen this module before. The one in the center, this is the HC05. They're dirt cheap. Generally, I mean, they're not tiny, but they're small enough that you can generally hang them off even small robots to get an interactive session. It works really well. It's got reasonable speed. They generally work up to 115K. Occasionally, you get some of them. They're not all the same. There's quite a lot of clones around. Some of them will work at 230K. Occasionally, to configure these when they're disconnected with Bluetooth, you can use an AT command session. Sometimes getting into that AT command session takes a bit of patience and Googling. There's quite a lot of pages about setting these things up. The couple of things which are probably problematic. One is that although it works well on Windows, Linux, and Mac, it doesn't work at all on iPhone, right? So iPhone's got this is classic Bluetooth. They're using something called the Serial Port Protocol, or RF COM. And iOS only supports certain classic profiles, Bluetooth classic profiles, and the Serial Port Protocol is not one of them, right? Especially if you've got a low energy device. It's not too bad, it's not a high energy chip, but it's not designed for super low energy. So what that's driven is a big push towards Bluetooth Low Energy, right? Because Bluetooth Low Energy is supported on iOS, and that's probably what's caused a big sort of boom in microcontrollers supporting this, either with a separate coprocessor or on chip for chips from TI and Nordic, for instance. It's not particularly fast in my experience, right? I mean, in theory, you can get up to 50 kilobits per second. I've never seen that. Generally, you're talking about, less than 10 kilobytes per second, assuming you got what's something called BLE Performance, which supplies this thing called DLE, which is large packets effectively. So, I mean, the reason for this was developed originally was to optimize power, so that it's all based around packet transmission and minimizing the packet transmission. Now, the way they did that was they avoided creating a serial interface. This isn't really a serial interface. So let me just talk a bit about that. So effectively, it's got these things which are a bit like shared variables, right? And so you can set up a bunch of these shared variables, and one might be, you know, the battery voltage. Another one might be the run time. You might have another characteristic, which is a description of the unit, and another characteristic, which is a version number. And you can individually read and write these characteristics. And the protocol to do that is called GATT. So that's the terminology. And this forms this sort of tree. And what you end up with is, if you've got some sort of sensor, for instance, it's got various services underneath. And each of those services, for instance, there might be a device description service, has several characteristics underneath those. And each of those characteristics can have an optional descriptor, so you can effectively figure out from a mobile phone or from a test tool what the shape of those is without having any documentation. And it's got, each characteristic's got read and write and notify and indicate. So read and write is self-explanatory. Notify basically lets you know when the device's, the target's data has changed. So if that variable's changed, say if it's a day of the month, or if say if it's a battery voltage, whenever that changes, it'll send it back up to the sort of central, right? Indicate is sort of an ACK system, so that you know you've definitely written. So it's a bit different in terms of conceptual model, and this is just a different view of the same thing. So you end up with these services with individual characteristics on. They've got each of these characteristics got a value and maybe some descriptions. So how do you use that from a hobbyist point of view? So there's obviously two options here, and I've shown the third bullet point here is effectively you can use maybe both of these. So you can either use it as a serial adapter, even though it wasn't designed, the Bluetooth special interest group hasn't got any standard setups. They call them profiles. It's different from Bluetooth Classic profiles, though. They haven't got any standard definitions to use it as a serial adapter. But that doesn't stop you having one variable as a write, gives you serial port write, and one variable is your serial port read, or even you can see systems that have got a single characteristic that you can read and write to, and that effectively read and write multiple blocks, and it effectively acts like a serial adapter. The second one is to use characteristics. So if you've got a Bluetooth microwave, you know, the one characteristic might be to start the microwave, another characteristic might be to stop the microwave. There might be a time remaining. There might be a time set. There might be a configuration of the microwave as another characteristic. You can also mix the two. Now, this depends on what sort of platform you go to and sort of how we link that to Forth. So let's just take the case of the serial adapter. So I've got one here, and if you compare that, I'll show you these in a minute, but this is the Class Bluetooth Classic, and this is what's a HM19, and you can get the tiny little board. You can buy those on Amazon or eBay or AliExpress, or you can get one with pins on. So this is I don't know what this is. This is probably a TI part with software on that just acts like a serial board. So you've got TX and an RX, and it sends it over these characteristics, right? Now, from a PC point of view, right, if you're on Windows or Linux or Mac, how do you get this to talk? If this is on your device, how do you get it to talk? So you've got effectively two options. One is some of these manufacturers supply a driver to make it look like a virtual COM port, right? And on the surface, that looks like the easiest option. My problem has been that these random pieces of hardware often are poorly supported in terms of drivers. And whenever my Mac or Windows machine warns me that the driver's not signed, as I show this dialogue, it always makes me nervous, because that's the sort of land of kernel crashes and rebooting PCs, right? So I'm always nervous about installing random drivers off random manufacturers. The other way is just to talk to the characteristics. So this has got characteristics. Windows over core Bluetooth, Mac over whatever it's called on Mac, and Linux on BlueZ. There's effectively an API we can detect this is advertising, bind to the device effectively, or link to the device, and then just read and write those characteristics. And on Android and iOS, it's a similar process, right? You just read and write the characteristics. There's maybe a bigger talk I've got in the future about if you're running on Android, there's actually tools that you can build a simple GUI, I think done by one of the universities, where you can read and write to Bluetooth devices. They're working on they've got iOS running, but not over Bluetooth. So this is one example. This is an Arduino Nano clone. So the Arduino Nano, the original Arduino Nano is an 80 mega 328p. So for instance, I've got one of these running on a robot. It's running FlashForth, and it's got a TI part, which I think is this one here, the part next to the antenna, which is acting as a serial adapter. It's actually also doing the USB to serial adapter as well. So you can connect over this. You can use AT commands to configure the Bluetooth adapter to whatever speed you want, and then you can talk to this over Bluetooth LE, and it acts like the serial port of the Arduino Nano that you've normally got. There is a problem. This chip actually supports BLE5, the CC2540. The software they give you is actually just a Bluetooth 4 image. Now, because it's Bluetooth 4, it's only got 20 bytes per packet, and you end up with a problem keeping up. So if you type words in FlashForth, it won't print everything, which is a bit of a pain. You've also got there's other people. So this is the HM19 device I showed, which is TI. This is Fanstel. These aren't particularly, you can buy these off DigiKey. They're not particularly expensive. These using the Nordic chip underneath. Nordic themselves actually do this thing called the Nordic UART service, which basically is just a standard characteristic number. So all these have got a 128-bit number that represents that characteristic. So anything built off Nordic tends to use a Nordic UART service. You've also got these. So the other approach is these things. Now, this Arduino Nano 33 BLE uses this U-Blocks chip is effectively a Nordic chip which does Bluetooth. The problem with this is, unlike it's not particularly well supported on Forth out of the box, and secondly, the Bluetooth libraries are obviously all written in C. So the best way of approaching this, now I know I'll put the link. What I did for this chip, it's got a reasonable amount of flash and RAM. It's just ported pForth. Right now, pForth isn't ideal for embedded targets, but it runs on it. And then I just added some core words that allowed me to define those characteristics. So what I want to do is define some custom characteristics. Some of them might be the serial port, and I'll link it to the Forth interpreter. But effectively, this allows you to define characteristics, any characteristics you want, and the descriptions in Forth, right? And all I've done is linked pForth, given some pForth core words, and linked those to the underlying Bluetooth stack. So that's sort of the other approach. Now, so there's a yeah, I put the article. So I put the links for that project there. So I just thought that would be a having done a bit of Bluetooth stuff, especially Bluetooth LE. It is quite a nice technology, but it's a bit more involved than just a standard serial port. Okay, so that's the brief version. I've actually got another talk about that goes into a bit of more detail about debugging this. Talking about just as a final thing, if I stop sharing for a second. This here. I should take my blurring off, right? This is this is done by. This is the. This is this thing. This is an Arduino. Let me turn my blur off. Stupid. Modify. Choose virtual background. None. That's better. Right. So this is a Arduino Nano. It's the Arduino Nano RP2040 Connect. Right. So this is a Raspberry Pi Pico from Arduino with a 2040. It's got the Nano footprint rather than the Pico footprint, but it's also got that U-Blox chip in there. That's got Wi-Fi and Bluetooth, both Bluetooth Classic and Bluetooth LE. So you can get these for about under $20, and that'll run. I'm sure it will run both ME Crisp and Zepto Forth is another one that runs on the Pico. And because it's got a separate Bluetooth chip, a separate Wi-Fi chip, you haven't got the problem of having to configure all your own characteristics and having a big Bluetooth stack that you've got to somehow imagine how to link into your core forth. I noticed some chats about reading ELF files. I've done that in the past as well. It's not overly unpainful process, but that's just interesting because this is sort of a Pico type device, but with that. The other approach, obviously, is what I think Peter Jackety had done, which was he just on that board that he's got on the the Pi Maker Pico, as well as an SD card socket. There's a socket for an ESP01, I guess it is, and that's obviously allows you to link via Wi-Fi rather than Bluetooth. I'll stop talking now, and if anybody's got any questions.
Rob, can I ask you something?
Yes.
You hear me well? Yes.
Yeah.
I have used not yet in FORTH because although I have programmed for many years in FORTH on older platforms, I did not found it yet, so I've never used it on recent platforms. But I've used BLE on a Node MCU without any problem. And directly in Windows 10, I don't needed any special manufacturer drivers or so. I got immediate perfect connection. The only problem I have is that the Windows 10 creates two virtual ports, one for transmission and one for receival. And I don't know if you have experience with that and or a solution, because for the current applications where I send data to sports scoreboards, it is a one-way transmission and that works perfectly. I just have to open one serial port on the Windows machine and send everything. But for other applications, which for example could use existing software packages from other suppliers, manufacturers or whatsoever, who use, of course, one serial port for both transmission and receival, I have not yet any possibility to interface that wirelessly to some hardware. And if somebody
as I remember,
the solution would be interesting.
Yeah, as I remember, Node MCU is a Lua-based solution. I think I've got. Is that correct on the device? Yeah. I think I've actually got one of those around here somewhere.
But I also use the same software.
So what it'll have, the Lua interpreter is written in C, and then have linked it to the C BLE libraries, right? And they'll be then they'll have set up two characteristics, one for read and one for write. And Windows 10 must have a built-in driver for node MCU. And I think it'll be that built-in driver that's binding the two. There'll be two characteristics, one for read and one for write. And it'll be binding those two characteristics to virtual COM ports. So I think, having not played with it on, I mean, I've got a Windows machine, but I haven't played with a Node MCU on Windows. But I think your two choices are either to get a different driver, change the driver that's talking to, because they're not serial ports at all. It's only emulating serial ports over the Bluetooth LE, as I'm sure you know. So I think your choice is either to get a different driver, or have a program that reads and writes those characteristics in the background. So you can do it in user space as well. It's a bit easier on Mac and Linux, but it is possibly Windows. What you can do, those Bluetooth characteristics are readable, writable from the user space. You could have a program running that read and write from user space, and then created a virtual COM port on the other end for other programs to connect to. You can actually do it on Linux and Mac. You can actually, there's ways of doing it with on the command line actually. On my day job where I use Bluetooth LE. The Windows, most of that's for Android and iOS, right? They're embedded devices that you can configure from Android apps and iOS apps, which is the reason we're using Bluetooth LE, because Bluetooth Classic doesn't work. The Windows test app we run, we talk directly to the characteristics from Python using the Bleak library. But you could create a virtual COM port from that. It depends how much effort you want to spend, right? It's maybe a day or so to set that up.
Yes, but the thing is, for existing applications on Windows, I don't want to change anything or add something. The question is there something that I can change on my? You
need a different driver that binds those two characteristics into a single COM port. The problem is the driver that's running, the serial port driver that's running on the machine.
The Windows driver,
Yeah, I mean, it might not even be written by Windows, right? The one that ships with Windows might be written by somebody else. So, a lot of drivers are certified by Microsoft, but they weren't originally written by Microsoft. I assume that Node MCU must have got the driver for that certified by Microsoft included in the driver distribution.
Okay, thank you.
Okay, Robin, thank you very much for your interesting talk. Amazing.
I'll generate a PDF and share it on the FORTH 2020 group as well, so you can have a read through the PDF.
Fantastic. So the next participant is Vladimir Gumenuk.
Yes, it's okay.
I don't know. Okay.
VOA is also acceptable. It's very short
Fantastic.
and easy to pronounce. VOA.
Well, this is FORTH in 64 bits for Windows.
Yes. Can I share my screen?
Go ahead.
Today I would like to present my FORTH system that was developed during last 2 years. It has several cool features and I think it might be interested to the community. Here you see the project on the SourceForce page. The link is available in our Facebook group. It is written in C, C++, and assembler from scratch. And the FORTH system is written in FORTH and bootstrapped on the fly from source code. And it provides the capabilities to load system API from on the fly. And also it supports native callbacks with unlimited number of arguments. Well, actually, Windows operating system has, I think, no more than 4 arguments in callback, but for custom-defined ones, it could be useful. Also, it supports the real multitasking native threads with task word and many other cool features. And probably I'll now shoot a quick demo. This is a preliminary, this functionality is in preliminary stage, but still can be presented. So if you download this package, this is a folder structure. I've just created a shortcuts for easy access. So let's take a look on this. This is a very, basically this is do nothing demo. You see a ball on a screen and just I type a key and it stops.
We can't see that. We only see the SourceForge net.
Sorry,
page. I can't see your force.
Oops. I'm sorry. How can I share entire screen? I am not very experienced user. This.
And share again, and you can select which window. Yeah. Now it's okay.
Now do you see it?
Yes.
Yeah. Okay. So probably I have to start from the beginning. This is a structure of the project. If you download it from download section, I've just created a shortcuts to simplify the access. And now, do you see it? Do you see the system?
Yes.
Good. Just I have a quick demo. And here you just see a very simple demo application displaying a smile. But when I type assemble, this will try to generate an executable file. For now, as the problem that the information about the methods from DLLs is lost and my code generator has no idea what to do with them. So I just manually fix it. And this code is the generated code from the console demo, as I just showed you. And here the batch file. So, and we have here the executable file. It's not recommended to start it from File Manager. So I'm going to start it from Explorer. And here you see the same program just compiled into executable, and now it is separated totally from the system. And well, basically you can give it to your friend. So this was a quick demo of functionality. Now I would like to take a look on the source code of the system. As I said, it was written in C initially, but when I decided to add multitasking support, I incorporated everything into a single class. So what you see is primitives, very simple pieces of force words. This file implements all primitives that I needed, and as we are not limited to hardware, we can extend and to add as many primitives as we want. You see, they are implemented in very tightly Basically, one primitive, one line of code. And here you see the initialization function to build everything into the dictionary. So all primitives with the help of this function are compiled into the threaded code. And this is a special, let's say, function. This function is used to generate object code, to generate assembler listing for every particular primitive. Many of them are not implemented yet, and that is why the functionality is in preliminary state. Let's go a bit down, and here I realized that to bootstrap the FORTH system from scratch, I already need to have another FORTH system, because I didn't have one, I decided to implement manually what we call outer interpreter. And you see on the left part of the screen, it's constructed FORTH interpreter in C style, in C. It uses the same primitives for initial loading and compilation. And on the right side of the screen, you see exact routing implemented in FORTH, just for reference. And obviously, I needed to manually fix all offsets for branches. So now let's take a look at the core. Here in this folder, this folder contains the full source code of the system. Basically, bootloader reads this file, and here you see the list of the same files, right? And it loads them one by one and invokes this routing. And in this way, all system gets compiled into the threaded code. I choose direct threaded code for implementation. So let's take a look on a very fast file. I'm going to explain only first line. You see here how I define the colon. This is a basic word to define other words. So this line is inserted by bootloader into the tip buffer. And what happens next? The system is in execution state. It means that the header word will be executed. The basic semantics of header is to fetch the next word from input and create the header in dictionary up to CFA. The system is still in execution state, so this words also will be executed, and it's obvious that the state will be changed to compilation, and this part will be compiled into threaded code into the body of a colon definition. Next word as I think all you know that this word is an immediate word. It will be executed, and the interpreter will be switched back to execution state. So from this point, the colon is defined, so we can continue and use it immediately to define the next words. Here I define the compilation word, it's a comma, compile, some helpers. Finally, here you see the definition of semicolon. It's a bit long because it also grabs some metadata of the words and stores it in flags field. So basically, in this file, all words, all basic core words are defined, and you see here the command. From this point, I can start to command the code. Well, I'm not going to explain every word in this file because simply don't have a time. And since that, I have the possibility to implement all the system in forth. This is just a beginning because after that, I needed to implement strings handling, numbers, exceptions, floating point stuff, local support and vocabularies, and obviously WinAPI loading. I would like to mention about the vocabularies because this is very important milestone in bootstrapping for the system, because from now we have the controlled search order, and it means that the basic words like find and header also must be redefined. And moreover, all words that depend on these words also must be redefined. And you see here the redefinition of all words that was previously defined in early stage of bootstrapping. It's create, constants, variables, and so on and so on. After that, the final step is to define our core interpreter. It's a compile word and interpret word as you saw before. Once all of this done, we are ready to define the entry point of our system, and this is a WinForce. It does very simple things. It checks whether the tip buffer is not empty, and if it is not, it invokes interpreter, and after that, it goes to the infinite loop to interact with the user and again to interpret the user input. And then on the final stage of bootstrapping is once we have everything compiled into the dictionary, we have somehow to pass the execution from bootloader to so-called inner interpreter. And I just use this word A0. What it does, it just in case establish execution state, then set up stack pointers, take the CFA of our entry point and use internal primitive to assign the internal code pointer to it. And after this, the execution will continue from this point. And this happens every time you start the system. So basically, this is it. It has already many words. So this is the memory layout of the system. It is a single 1 megabyte block of allocated memory. It is, by the way, unique per native thread. So if you create a new thread, every thread gets its own forth system, but the dictionary is shared. As you see, here there are special Guard pages. Each block or each area has different access attributes. For example, a dictionary has access attributes execute, read, write, and the rest have just read, write. And the Guard pages that are inserted between areas have attribute no access, and it makes the exception handling is very easy. What I mean, so if let's say I do something like this, the exception will be handled and it will be passed to a forth system, and the system is still in working condition. So like this, let's say. Next, I would like to present the structure of words. There are several types of words in this system. So the ones that defined with colon, so-called colon definition. Here is a structure. It's name, NFA address, link to previous word, flags, and here you see the primitives compiled into direct threaded code. Create does. It has very similar structure, but the CFA contains do, does, doer, and the branch address where to continue execute. Do, does just load the address of PFA on the stack and jumps to this address. It's very simple. And for variable constants, again, same structure, name, link, flags, and do variable doer. It just loads the address of PFA and exits. Well, I really apologize for this slide. It's too much information. This is a structure of flags field. It's don't forget, I'm talking about 64-bit cells. So 24 bits first are used to store the flags with metadata information for the words, and they used in a subsequent object code generation. And this is just general helpers, the number of locals, if any, the number of parameters, it's exactly the number of cells for colon definitions, and unique primitive ID. Only primitives have this field, have some value in this field. The rest contains 0. So maybe I have to present some examples from, okay, let's take something very simple. It's test, it works. Okay. And this is yet another unique feature that this system has. This is, I call, integrated direct threaded code debugger. What you are looking, this is actually from left to right is a return stack with the pointer where we are. Central part is occupied with threaded code. It is decompiled. So here you see addresses, and here the values under these addresses and the decompilation. And again, where we staying are. And it's pretty obvious on the right, we have a return stack. Okay, let's try to go to our test. This is our simple test example that I just defined. What we can do with it, we can, by holding Control and double click, I can set a breakpoint here. And then I can run it. And now you see that we are staying here. F10 to go forward, and you see the on data stack, the items, the numbers. We can go if let's say I would like to go deeply, I can press functional K11 and I can go through all of these things again and exit. And if I continue, I will stop at the same interpret word that I just demonstrated. Can I type exit? Yes. This is a console at the debugger, so it's absolutely normal. What else? We can use a single step debugger. Like this. Sorry. This is because, let me try from scratch again. Yeah, and here we can again just pressing arrow keys to trace. So here it is. I don't know how many time do I have. So probably I have to stop on this and to listen to questions. Otherwise, I can continue with this example. This is basically the force calculator. It was written in force. You can switch the input base. And what is most important thing, I implemented this specially for me. Let's say I start input in decimal and I forget, and I would like to continue input in hexadecimal, so I can just switch the input system and to continue, right?
Vladimir, this is amazing. We are very happy to see your presentation. It was excellent.
Thank you. So all source code, let's say regarding calculator, you can find here, callbacks, graphics demo, library, this is a small subset that I just implemented. Here is a serial communication class. So for those who have hardware and you can connect your hardware to serial port and continue development in FORTH using this. It's working. I created it for my personal investigation. It grabs accelerometer data from our device. You can adopt it. What else? Test. The system is not almost non-standard. The mass, the double cell mass, floating mass are pretty much standard. What is not standard is the strings handling. They are zero terminated. And what else? The dictionaries is a bit non-standard. The rest is pretty much standard.
We should ask the members if they have any questions for Vladimir. Are there any questions?
I have a question. I've just downloaded and unzipped it, and it looks excellent. How do I load, for example, calc.f?
Calc.f?
What's the thing? I've tried to include.
Just include.
Yeah.
Example.
Okay, you need to put the full path, of course. Yes.
Calc
F.
Yeah. Oops.
Okay, you misspelled that.
No, it's okay. It's okay. This is why. That's why, because I have here hide console. So you can command hiding console, and you will see in this case.
Okay, thank you. Perfect. Okay, I will have a play with that. It looks really good. I have to say, it looks really clean and simple and elegant. And that appeals to my fourth senses.
Yeah, I try usually to put as much commands into the code as I can, because after, if I wouldn't do so in several weeks, completely, yeah. So let's say this is my own OP, object-oriented extension, and there are a lot of documentation. So everything is very well commented, so you can, I think everyone can understand, can read it.
One other question, quickly, how do you recompile it?
Recompile, sorry, what? Itself? No, I use Visual Studio to build it.
Okay, that's what I meant. Okay.
Oh,
Yeah.
Vladimir.
Yep.
Vladimir. First off, Yakoyo, right? Well done. But does it run on Linux?
Well, unfortunately, no. This is because of very non-trivial things, like callbacks implementation and the native threads implementation. I can show you briefly, but it's actually depends on it depends on Windows stack frame, and I'm unfortunately absolutely not a Linux guy, so I just don't have a knowledge to convert this. And the same with multitasking. So it heavily depends on a so-called thread local storage Windows section.
Okay, Vladimir, this is no problem. We need to continue with the meeting. I thank you very much for your excellent presentation.
I have one last question.
Yeah, please.
If it's short, okay.
Okay. Have you tried this under Y?
Sorry, didn't get. Could you please
Y
repeat?
is an API layer for allowing running Windows executables under Linux. And all I have to say is I'm very impressed by this, but because I'm a Linux user and my Windows installation is very old and probably insecure due to never having been updated in years, I'd like to be able to run it under Linux, but due to being tied intrinsically to Windows, have you tried running this under wide so that Linux users can run it?
Okay, but now it's time for another presenters because we are out of time. So sorry, but this will not be answered. Vladimir, I invite you heartily for next meeting or other meetings. You make a second part because this is very interesting, and no problem. We welcome you very much to make a second part of this. Okay.
Okay. Thank you. Sure.
Thank you very much.
Thank you, guys.
Now the next participant is please unshare your screen, Vladimir.
How? Sorry, I'll stop share.
And thanks you again for your kind and letting us put Rob in the front because he was just arriving from a trip. Thank you. Now it's turn of Frédéric Segard from Canada. He's going to show us 6502 single board computer, a very interesting application with the hardware. This is hardware.
Oh, hello everyone. I'm a bit nervous to speak to a lot of people at the same time. I'm not used to doing that, so I hope I won't stutter too much. Let me share a bit my screen. Okay, so share. There, are you seeing the shared screen?
Yes.
Okay, well, that's weird. What's going on? I'm not seeing it. What are you seeing right now?
I can see it.
Seems like
yes,
the first line, MH6502, hardware comes forth.
Ah, okay. All right, good, perfect. There's something wrong with my display.
That's probably we see the presentation and
okay.
You probably see the PowerPoint.
Yeah, exactly. So you see it full screen, right?
Yeah.
Okay, so basically, well, the MH stands for micro hobbyist. It's the handle I'm using on Reddit and stuff like that. So I am a hobbyist. I'm not a professional, although I did study electronics 30 years ago. And so basically, put things into context, started to do this during lockdown. Of course, I was inspired by many people who did 6502 by Ben Eater videos. And so I started to relearn electronics, basically, because I had forgotten almost everything. So I had to purchase tools and components and whatnot, and of course, try, fail, try, and it works. So I had many iterations of breadboard. This is my first try, and I followed wire by wire Ben Eater. And then I started to add stuff progressively and add an LCD, a bigger LCD than what was on the tutorials. Decided to, I got this old keyboard, let's try to add another keyboard besides PS2. And it worked, but the keyboard itself was problematic. It had sticky keys, so I had to ditch that problem, that solution. And then I incorporated video with the TMS 99188 chip, VDP. And as you can see on the screen, well, we can't really see it, but well, it's there. And then another version and another, because each time I did a new PCB, I recreated a new version of what I wanted to do. There you see with the connectors for the PS2 keyboard, mouse, NES controller, and the serial port. So I started to do, I don't know if you see a side-by-side of me and the presentation, but this is my first revision of the board, which is basically very trimmed down version of the components that has a CPU, ROM, RAM, and the serial port. And the slots that you see up there are the what was it, RC6502 compatible bus, which I never really used because I had to buy or create new bus cards, which I did not want to spend time on. And at the bottom row is the breadboard connection, which I actually could connect breadboard directly on it. So this is what it looks like, all assembled and connected to a breadboard with the VDP on it. This board actually had a few errors. I don't know if you can see it, but there's actually a bodge at the serial port. I actually inverted the clock signals on the ACIA, and the reset button was reversed. So I had to re-bodge that also. And then I said, okay, that's fine. Now I wanted to expand my my computer. So I needed sound and video, and I wanted to incorporate the I/O. So I did the Rev 2 version, which is a stacked version. So you have the basic I/O that I had in Rev 1 on stack number 1. Stack number 2 is the I/O, which has the PS2 and a NES controller and LCD connector, and the rest down at the bottom is the I/O for SPI, which I've never got it to work because the footprint of the PCB was the wrong one. So this is the actual stack. I don't know if you can see it. I think it's nice. I mean, it looks interesting. I started to unsolder the components for Rev 3, so that's why it's quite empty right now. And there was an issue with the clock also. I did not buffer the clock properly, so each time I probed it, everything was okay. But once I unprobed it, the computer was going haywire. So something was there was an issue with capacitance somewhere, and the probe fixed it when I probed it with my scope. Kind of weird. So third on the stack was the sound card, which had 3 AY 38910 PSGs, which were configured stereo, left, right, and center channel. And the fourth stack had my video card, the VDP TMS 99188 or 991828A, which would be component instead of composite, but it would accept both chips. And I had a bottom stack, stack board, which would connect to the breadboard if I needed to interface it. So these are the boards that I had made. Unfortunately, it was a failure because of the obvious errors that I mentioned afterwards. So I redid the breadboard, made sure everything worked. In the history, you saw that in previous images. So I came to Rev 3. And Rev 3 is actually made to fit with a particular case. I don't know if you can see it. And Rev 3 was actually quite one of my biggest works of art, if I can say so myself. All the ports, I have 2 serial ports, a third one actually which is TTL and not RS-232, and PS2 keyboard and mouse, and 2 NES controller. And the reason why there's a specific shape to that PCB was because I wanted to put the buttons in the front of the casing, and they had to slot in at particular places, and and there's a space also for the LCD. But when I decided to, as you can see, there's a connector for a bus connector for a daughter board, which I wanted to create the audio video board that would stack on top. When I started to design it, I told myself, well, is there a particular point to do this? I might as well remove some of the components that I'm not using, like the third serial port, the bank RAM, which I wasn't really using. So I removed those, remove the button location so I could put more space to the for the components, and hence came Rev 4 with basically the same components, but with the video port, which is on top left, and on the bottom left is 4 PSGs. But this time, instead of doing stereo, they're all in mono. I told myself, do I do stereo or mono? It all depends on who you ask, but I thought that mono would be more conducive to the era of 1980s computing. They didn't really have stereo back then. And plus, the TV that you see behind me is only mono. So I said, well, might as well use mono. So I was really worried because of the 5 boards I received, 2 of them, the VCC and ground planes were shorted. And the first one I tested was shorted. And I told myself, I can't use these. I mean, the whole batch is scrapped. When I tested the other boards, it turned out that only 2 of the boards were shorted. So at least I was able to create one functional system, which actually made me proud, because as you can see, everything worked, and the keyboard and mouse and everything. So basically in the specs, well, you have the 6502 CPU, which normally ran at 2 megahertz, but I managed to push it at 3. When I tried to push it at 4, the VDP started to garble up, but then I'm not actually respecting the timings of the write to the VRAM. The glue logic is all EEPLD based. I also have a priority interrupt controller made with another EEPLD. I got 30K of RAM, which is actually a 32K module, but I had to segment it so I could make room for the 2K of non-volatile RAM, which is actually also a real-time clock, 32K of ROM. I've got 2 ACIAs, which are the serial ports, one configured data terminal equipment, and the other one is data communication equipment. And I've got a combination of 65C22 VIA with a microcontroller that takes the input of the PS2 keyboard mouse and does the translation, and you get the proper ASCII codes instead of doing the decoding of the scan codes that's usually output from the keyboard, and dual NES controller ports. The video, like I mentioned earlier, it's a TMS 99188 chip, and I've got 4 PSGs. For my intent was to do a nice music box, and in the future updates, Rev 5 maybe, there's going to be, I want to make it run at 10 megahertz, so I'm actually running, I'm doing a test circuit on a breadboard to do some clock stretching or wait states on the CPU, for the CPU. Either I'm sticking with the 6502, or I may go to the 65816. That's still in question. I'm probably going to re-add the 512 extended RAM. Additional PSGs, maybe. It might be overkill though. And I'm going to incorporate the 2AA instead for component output. Or maybe I'm just going to scrap that and try a VGA circuit instead, because the quality is actually a lot better. And also there'll be a SD card reader or maybe a compact flash reader, which might actually be easier to implement because it's directly addressed on the bus. More, oh, TBS, no, it's TBC, sorry. To be confirmed for the next, for more I/O, I guess. So in the BIOS, if I stop sharing this thing, okay, where's my little button? Stop sharing, come on. Hold on a second. Typical Zoom stuff, right? Screen stop sharing. Okay, good. Now I'll just open the terminal window. So when I reset the board, we probably heard that it's playing a little music. I don't know if it was loud enough. You can see the time, which is the approximate time of where I am right now.
You're not sharing your terminal. That's
I'm not?
Sure.
Oh, okay. Share terminal, share. Thank you for letting me know. There, are you seeing it now?
Yep.
Okay, good. So in the, this is my monitor program. And if I type, well, I should actually go on it physically, there. And I type help. I have all my commands that are there. And sorry for the scandal, it says basic, but eventually it's going to say forth. So right now I'm pointing to address 0. And if I do a memory dump, I'm going to have all the memory locations displayed. I can go to point to address 8000, which is the beginning of my ROM. And I can either show the memory, or I created my own disassembler by myself without any help. And I've got this, the actual code for my ROM. And I'm actually pretty proud of that. Other commands are like the fill commands, which can fill a region of memory. Load and save aren't implemented yet. Oh yes, load is. It's actually a hex, Intel hex input from the terminal. And right now I'm typing from the console, but I actually can go on the keyboard and type in the command from the keyboard that's on a PS2. So both our inputs are valid. So I can stream data to a particular port. For example, if I'm sending a stream to the ACIA, I want to send, or a via port, I can actually stream. Actually, does that help? Does that help? No, it's not. I haven't implemented the help on the stream yet. But clock, I can read or set the clock. I can do fill, find, help, load, memory. We've seen that. The peek and poke, which is like classical Commodore 64 style read and write to a particular memory address. And yeah, that's pretty much it. Now, my next thing that I want to do is to try to implement Forth. And that's not going to be an easy task because I'm not an expert at either assembler or especially Forth. And I have downloaded Alexandre Dumont's Forth, which is right here. And so I'm starting to look at the code. There's a lot of macros in there, so I have to start to wrap my brain around macros because I haven't used macros in assembler yet, and I probably should have to save a lot of headaches from the past. I've also looked at the FigForth in the source code and also TallyForth. Now, I'm not sure which I'm going to use. Probably going to do a combination of one or the other, or if you have any suggestions on other fourths. And anyways, I know I'll be asking Alexandre more help to discover his fourth, because I'm going to start with that because it's a more a simplified version of the others that I think I can better comprehend. So that's pretty much it. So I don't know if you have any questions.
I don't have a question, but congratulations. What I've seen is amazing. You must only sleep by micro sleeps or whatever. Because it seemed that you started 2 years ago, and if you have done all that, and you started your presentation with saying, "I forgot everything about electronics," well, I don't think that is that we can believe that. Really amazing, and congratulations. It's impressive from my part. Great. Okay.
Thank you.
I agree. I agree to that. Very well said.
Congratulations, Frédéric. Yes, the hardware part is impressive indeed. I also started with Ben Eater videos, but I just stayed at the breadboard stage, and I only built one breadboard, so it's the one I keep running, and I don't know anything about PCBs and oscilloscopes and this kind of thing. So, but on the other side, I went more on the software side, so I worked on FORTH.
Well, Alexander, you are the next one. Are you ready?
Well, yes, I think.
Well, fantastic. So I present Alex Dumont for second time in the group. We are very happy. And sorry, Frédéric, this was amazing.
Indeed.
So any next meetings, when you have any news and you have your FORTH running, come again. We show it.
Can I just add? Can I add a very quick comment?
Yes.
Yes.
Have you tried? You said you had 2 printed circuit boards with shorts. A technique that somebody showed me a long time ago is take a 5-volt 100-watt power supply and power it up with that, because a short usually is a tiny little piece of copper that's got in somewhere where it shouldn't, and they usually just pop and it all works. Just a thought.
Oh, that's interesting. Yeah, I'll try that. I'll try that.
Yeah. A word of caution: you might blow some tracks if that short is too far away and you've got some narrow tracks. So I tend to apply that very close to where I think it is. But most of the time it's just a tiny bit of copper. You can even put control the current. Just put an amp through there or whatever. It's not going to blow it, and then go along with your meter and you'll be able to measure the voltage drop, and you go, aha, here it is. Amen on it.
Well, okay. I have nothing to lose at this point.
Exactly. Yeah. Hardware. What can you do? It's excellent stuff.
Well, okay, guys, we continue with AlexForth for 6502. Welcome, Alex, again. This is your second presentation, and we are very happy to listen to you.
Okay, can you see my screen?
Perfect.
Yes. Okay, fine. So I'm going to give some updates of my development of AlexForth for the 6502. Okay, so this is the content. As an introduction, AlexForth is my own implementation of FORTH. It's not following any standard at this point. I implemented it from scratch for my 6502 breadboard computer. So this is the one that we can see in the corner. It's a direct threaded code. It's written in 6502 assembly and in FORTH, and it's assembled with a CS65 from the CC65 suite. So that's for the one who, if you take the source code, that you will need that to build it. For the one that did not see it, I did a presentation in this FORTH2020 group in December. So here you have the link, you can see the presentation. And this AlexForth also runs on the Cerberus 2080. So Cerberus 2080 is a modern retro computer. It's a single board computer as well. It was designed by the Byte Attic. It's open source hardware. It does have 2 CPU. So one is a 6502 and also a Z80. of course, my AlexForth only works on the 6502. And it also has a PS2 keyboard, VGA output, and SD card, but I don't support the SD card at the moment. So some updates on my developments. First, some dictionary updates. Since last time, I've implemented some new words and new mechanism that I was not very familiar with at the moment, at that time, like value and to, constant, postpone, defer, and ease, also question do. I've also written the comparison operators, and I've also implemented a way to output with .s and dot, either with a sign numbers or non-sign. And I've added some stack manipulation pointer, stack pointer manipulation. So SP fetch, SP store, RP fetch, and RP store, which I found could be useful if you want to write some word for tracing and debugging. And also I have rewritten my create and does implementation to be more compact because it was not very efficient. I've also implemented number-based support. So now the user can change between decimal, binary, octal, and hexadecimal. There is a variable called base. And at the moment, I only support base 2, 8, 10, and 16. So I have not even tried to put something else in that variable. And also I have implemented some prefixes. So I know some are not fond of prefixes, but I find it can be useful. Also, I've implemented a somewhat rudimentary FORTH decompiler, the C word. So that would be the kind of output that it generates. So you can have the address in the thread, in the direct thread code, the content, which is the address of the implementation of the word, and the name of the words. When sometimes it's just an address, so it leaves the address. Of course, I have put some color for the presentation, but my computer is only use only a serial port, so there's no color. I wanted to talk also about some optimizations I've been doing since last time. First, why? Let's have a look at last time. Now it has changed, but last time the organization of the source code of AlexForth was a monolithic source file, so forth.ace, and inside that only file there was different kind of languages that were mixed, so different kinds of writing. So you could find some assembly code. So this is, for example, the code for next, and there are also all the primitive words are written in assembly. You can also find some hand-compiled Forth code. So it's basically there's the jump to the do colon word, and then it's all the addresses for the other words. And also there was a big string embedded in the code with the definition of all the new words. I call this the embedded Forth bootstrap code. And everything was in a single file. And when you build the source code, it would generate one binary, which is called forth.bin. It was a one-stage compilation. And as a result of this, okay, I've put on the slide like a representation of the memory of the computer. So at the top of the memory, you have the ROM part where the binary is loaded when you reset the computer. It's there. And inside you can see there is this bootstrap Forth code, which is the string. And when the computer reset, the first things that it will do is interpret and compile all whatever is in this bootstrap's Forth code and generate all the compiled dictionary for that. So the thing, what I've noticed is that it was taking a long time, and it was not efficient because it was time consuming and also space consuming, because you had to keep in ROM the bootstrap code, and it was also consuming RAM at the start of the dictionary. So I thought, how can I reduce this? First, what I did was try to measure this, because that was the first thing. If I wanted to optimize it, I needed to be able to measure it. So I defined this measure, which I called the boot time. The definition is the number of clock cycle from the CPU reset until the end of the bootstrap code compilation, which basically is when the user is shown the OK prompt. So there is a time, and it can take, at the beginning, with no bootstrap code, the boot time was about 3,000 cycles. So it's very short. But with the bootstrap code and the more code I added to the bootstrap code, it went up to 3.8 million cycles. Which if you think about a CPU at 1 megahertz, 1 million cycle is 1 second. So it was about 3 or 4 seconds. So, I mean, that's not a lot of time, but I was obsessed with that. So that's what I've been working on. And so I started to think, what really impacts the boot time in my computer? Of course, it's heavily related to whatever impacts the interpretation and the compilation of the bootstrap code. So obviously no bootstrap code, there's no time. And the more I put in that, the more it takes. So first, I started to think about some strategies to optimize this boot time. And later we will see the result of implementing some of these strategies. So some strategies I've been implementing was, for example, convert some words to primitive. And this kind apply to any word. So if I take some words from the bootstrap code and implement them as primitive, obviously they disappear from the bootstrap code. So it's faster because they are already compiled. I also found that some words like comma and C comma, which are heavily used during compilation, were not primitive. So I converted them to primitive, and that was a huge improvement. Then I thought, what about the dictionary lookup? Because when you interpret the words, find has to find a word inside the dictionary, and the more the dictionary grows, the more time it can take to find words that were at the beginning. Because the lookup in the dictionary, in my implementation, there is no hash table, it's linear. So I start from the end of the dictionary up to the first word. So here I took two strategies. First, I saw that you can reorder the words inside the dictionary. So the ones that are used the most, I had to try to put them at the end of the dictionary. So that did some improvement. Also, I thought, okay, there are some words that are used a lot and that are very small. So basically the one character words like colon, semicolon, fetch, store, comma are used quite a lot, and it's a waste of time to try to find them. So what I did was put some shortcut in my find implementation, and I just compare. If it's a colon, then the CFA is this one. So it was very fast. But there is a drawback to doing that, because I noticed that if I keep these shortcuts in the find word, then I cannot redefine colon or semicolon afterwards. So actually I kept this implementation of shortcuts in my find implementation, but just during the bootstrap compilation. At the end of the bootstrap compilation, I disable it. Okay, so another small optimization I did was to move some fourth variables to 0 page. So, well, it's a bit faster because 0 page access instructions are more efficient. And also I did some refactor of some word algorithm that were not very efficient. So, and also another strategy was to take the words from the bootstrap code and hand compile them into the assembly listing. So they would not need to be compiled by the compiler. And if we look at the result, by implementing some of these strategies, I managed to shave off about 2 million cycles from the compilation. And here's a summary of all these strategies, my feeling of the effort needed to implement them, and the impact of each of them. So of course, converting to primitive or refactoring words and converting them to primitive, well, it's a high effort because you need to think about it. But it gave a big impact. Reordering the dictionaries, it's a low effort. Well, it was quite an impact. And well, that's the result. But still, I was left with almost 2 million cycles of compilation. And it would grow as the more word I would add to the bootstrap code, the more it would grow. So I was not very happy with that. And that's where I was kept with this one. If I remove the word from the bootstrap code, if I end up removing all of them and compiling them somehow, it would be the end of the problem. So I came up with a solution that is, I would compile instead of in only one stage, in 2 stages. So what I did was I separated the bootstrap code in a separate file. And I separated the compilation in 2 stages. In the first stage, only the fourth code without the bootstrap code is built. It's loaded into ROM, but it's run into an emulator. So into this emulator, what I do, I feed the bootstrap.f file, source the bootstrap code, into the emulator as if somebody would be typing it. And so what it does, it's generating the dictionary, but instead of generating the dictionary into the RAM space, it's generating it in the ROM space because it's an emulator. I can do that. Everything is RAM really, so I can write in the ROM area. So that's what I do. I do that, and everything is automated. Then when we reach the end of the bootstrap file, there's something notifying the compiler, and the compiler extracts both part of the dictionary to a binary image file. So at this point, what we have here is the direct threaded dictionary already compiled in binary form, so I can extract it in a file, and the same for the RAM. Yes, let me explain why. There is almost everything is written in the ROM dictionary area, but not everything, because when I'm adding variables to the dictionary, they need to be kept in RAM. So that's why it's separated in 2 parts. So I extract the 2 files, and then in stage 2 of the compilation, what I do is, again, I rebuild the whole forth.s file, but this time, and thanks to some defined directives of the compiler, this time I change the behavior and I insert inside the file the ROM dictionary and the RAM dictionary in their binary form. That way, I end up with a fourth binary, which contains the fourth dictionary already compiled, and a small piece, which is the RAM dictionary, which when we boot, it will be at the first, each time we boot, this RAM dictionary will just be copied in place to the RAM dictionary. And last, and here, variables need also to be updated. So it's not shown here, but they're also kept in some place in the source file. So that was kind of tricky to do. but it's very efficient, of course, because I can reduce the boot time to from 1.8 million cycles to under 3,000 cycles again, which is almost instant. The user won't not notice that the startup time. Of course, what I gain is the boot up time of the computer is almost instant, but the compilation now is long. It takes longer time, obviously. So that was the part of the optimization. Well, I've got two slides about documentation, and that's it. I've added some documentation to my repo, with some usage example. I mean, it's more for myself than for the user. There's an example of using a FORTH decompiler, how to debug, trace. And also, I've added a page which I call the anatomy of compiled words. And in it, I've documented several sections on literals, conditionals, so how are compiled words like, for example, if I put if then else clauses in a word, this is how it is compiled in the direct threaded code. That reminded me a lot of Vladimir presentation, but with his debugger, because it's almost the same kind of drawings, but mine is just a documentation. It's not live in the debugger, unfortunately. About next steps for my FORTH. Well, the limitation of this FORTH at the moment. Last time I had only hexadecimal representation, so now that this one is ticked. Still, as a limitation, I only have integer numbers, so I'm thinking of how to implement floating points, but I find this very difficult. I don't know. We have to look how to do that. Also, I only have one dictionary, so I don't have any vocabulary handling. And the other points still remains. So there's no stack on the flow or overflow. It's only case sensitive. There's no mass storage, and there's no standard at the moment. And well, that's it. I don't know if you have any question.
Quick question.
Sure.
Is I see your stack is pointed in the 0 page. Don't you have a risk of not having enough memory? Because it's pointed at...
yeah, it's in 0 page. I think there will be enough, because one cell is 2 bytes. There's 200... I don't think I will run out of memory. I think I have like 128 bytes in the first page. So it's enough. I mean, Chuck always say that the stack should be less or less than 8 depth.
Oh,
so
okay. I thought that
but yes, there is a risk, of course, if you have words that leave things on the stack, and yes, it will crash. Yes.
In my experience, I have my own FORTH, which is 4-byte cells. I only, for individual tasks, other than the main task, use 128 bytes for my stacks that haven't run into a problem despite having larger cells.
Yeah, and also, I mean, I have not developed any application in my own FORTH, so the main project is just about developing FORTH and enhancing it. But to be honest, I'm not a user of it, or very, very limited user. So I've not run out of stack space. I mean, if you need 128 cells in the stack, maybe you have to think about your application. I don't know, but of course there is a risk of running out of stack space, but there is also a risk of running out of memory, because in my particular implementation, I only have 16K of RAM. So,
do you support recursion?
Yes, I do. Yes.
So there is a risk your stack will explode. Definitely.
Yeah, definitely. Yeah. But I mean, this risk will always happen because the hardware is very limited anyway. So if I were to go to more hardware, I could support more more stack depth.
I think it is very important to do bounce checking on the stack. Really, shit happens, and
I'm sure. Yeah, I am crashing it every time I use it, so maybe I should consider it. But that's not implemented at the moment. That was not one of my priority. All right. So, well, thank you.
Thank you, Alexander, very much. Very interesting. We have seen a large improvement in your force, and we hope to see the next vocabulary implementation and the other things.
Yeah, I also have another project in mind, so which would require doing another computer completely. So maybe I will work on that next. I don't know. I will have to share times.
Fantastic.
Sorry? No, it's not an 860. No, it's a R65C19, I think.
19?
Yeah, it's a different computer. It's like a version of the 6502 with new registers. It's still 8-bit, it's new register, and there are 16-bit registers. One I think is I, and the other is W. And it seems interesting for FORTH.
Yeah. Hey, Alex, so that particular one there, the Rockwell one, the 19, yep. That's all part of the ones that they developed for the modems that they did, you know, so I've got all the different chips. And they support threaded code because, you know, the first chips I used were the Rockwell chips and the 6511s, etc., the single chip micros. Does the 19 have the internal bit instructions and everything else? Because the 6511 was very good with being able to set memory bits and test bits and everything else just in one instruction.
Well, I wouldn't know. I have some documentation which I find kind of well. I don't know. I think there's very limited documentation, only the data sheets, and I think there are very few people who have used it. So I can't find anything in the forums and this kind of thing. It's very different from the 6502. So that's a project I have to start, but maybe I will talk to you if you when I start.
I've got plenty of documentations around so on all the different chips. So yep, I'll send you some.
Okay, thank you.
Okay. Yep.
Appreciate it.
Wonderful. Now we continue with the meeting, with this fantastic meeting. Everybody's happy to see so much information. So wonderful, all participants. And we had in the program Chang Luke or Holly. Are you now in? Are you ready? Are you in the group? Chang Luke or Holly, where are you? Mr. Holinepu, Chang Luke, hello. I saw him in the meeting, but it's not answering. Hello. Last call and the train will go. Ready, Chang Luke or Howerd Oakfoard with Colorforth? Last call for Chang Luke.
I'm not seeing his name on the list.
It's Holinepu, his name.
Ah, okay.
He has 3 different names. He writes me in Chinese, and then I need to, Holly, Taiwan. Yeah, he's there. Holly, can you listen? Probably he's sleeping. Oh, there he is. No sound. We can't hear. You are muted. Is this a presentation without sound? Haulinepu, hello? Well, I can't understand if someone can explain to us what is this kind of presentation without sound. If not, we continue to Howerd Oakfoard.
Hi, do you need somebody to translate for him? Maybe he didn't pick it up. Do you need somebody to speak Chinese?
We don't have this. No, we speak this in, we all are from different countries, but we speak English. We do an effort to speak in English.
No, I mean, he didn't understand.
It's not allowed.
No mic, no video. Just move on to Howerd, you know.
Yeah, no way to see that.
Okay,
Howerd,
yeah,
you are the next.
I'm happy to go ahead. I've made this presentation much shorter than the last one, so we can overrun and still only be a little bit late.
Amazing. Go on, please.
Holly, what's his name? Holly can have a go fairly soon. He's got a little time to sort out his hardware. Okay, I'll share my screen then.
Yes, in this case, when the participant does not speak English, there are other options. He can make a video, for example. We make subtitling. He can speak also in Chinese and tell me what this is about, but he did not contact me. So sorry for that, but I continue with Howerd. Hello, Howerd.
Hello.
Colorforth, second part. Go ahead.
Yeah, I'm just trying to pin my own image so I can see what I'm saying. That makes sense. Okay. Okay. This is part 2. So I intend to explain a little bit under the hood, as they say, how it works internally and a bit more about why as well. So, okay. So this is, as you all know, Colorforth. This is what the start screen looks like. And you'll see here, this is from April the 21st, which is not fully released yet. But there is I will publish a link to where people can actually get this exact code so they can try it out for themselves. Okay, that is the link, but I'll paste it in the chat so you don't have to actually type it in. If you do want to type it in, sorry, then bear in mind this is an underscore, otherwise it gets confused. Okay, so under the hood, and I want to talk about Shannon-Fano encoding, which I thought at first was Huffman encoding. And these are techniques where you compact text by using sequences of bits that are very short for the more common characters and longer for the less common ones. So this is what we have in the Colorforth system. This is what it uses internally. So you can see here, for example, that an A is represented by a 5, which is 101. And these first 8 are actually all 4-bit characters. So you can fit in your 28 bits, you can fit up to 7 of these first set of characters. RTOENANI are the first ones there. The other 4-bit character is the 0 or a null. More about that later. Okay, so you've got, first of all, the 8 4-bit characters. So as I'm sure you all know, ASCII has either 7 or 8-bit characters, and they're all the same size. But here, these ones, which are the most common letters in English, are all 4 bits. So obviously you get twice as many in there. So as I just said, you've got 0, all 4 bits. 0 is a null terminator. And then you've got R, T, O, etc. Now, the point here is that the first batch of characters has a prefix of 0, and that's highlighted in blue or cyan here. So then the next group of characters, you've got 8 characters that are encrypted by 5 bits each, or encoded 5 bits each. So S, M, C, Y, L, G, F, and W, and they have a prefix of 10. So what that means is that, for example, if you want to express an S, which is the first character there, you'll see there's the 8, 0, 0, 0, whatever. The 9 at the end of this, this is the, oh, yeah. Don't you love it when your keys just suddenly change the screen for you? The 9, I've lost my cursor. Anyway, the left hand digit here, I can't see the cursor. There you go. These 9s indicate the type or the color of the 32 bits. Everything in Colorforth is a 32-bit chunk. And the 9, I keep losing my cursor. It's so confusing. Okay, there is a type of token, which is colored white. And it's type 9, which is a lowercase string. So the 8 is a single bit there. Okay, so let's move on to the next one. So you can see here, this is how you encode S and SS and SSS, because they're all 4, all of those, the S is a 4-bit, sorry, a 5-bit string. 5-bit sequence of bits beginning with 10. That's the prefix. So what you can see here, if I can find my cursor again, here, okay. So you've got the blue prefix 10. So when the system sees that, it says, it's a 5-bit token. So I'll use up the first 2 of those bits because that's the prefix to know which type of token it is. And then you get zeros. And then the red ones here at the end are the 4-bit token, which is one of the initial ones, which is the one represented by an underscore here, which is a kind of null. I hope this is all clear. It's kind of hard to run through this very quickly, but what you're doing is you're not encoding it as a sequence of bytes like you do normally. You're encoding it as a sequence of bits, and you use the first bit to yeah. Can you hear me? Is everything okay?
Yes, perfect,
Okay.
perfect.
So, okay, good. So the first bit in the sequence indicates what the type of token is next. Is it going to be 4 bits or 5 bits? So if it's a 0, it's 4 bits. If it's a 1, then it means the next bit must be a 0, and then it's a 5-bit token. There's also 8 of those. So if I go on here, just to give an example, if I switch to the M's, which is the next character, M is represented by a 1. And you can see if I just toggle backwards and forwards, you can see what's changing is that the green field there goes from 000 to 001. So this is how the Shannon-Fano encoding works. And there's one more group of encoding, what do you call it, which is there's now 32 7-bit tokens. That means that you can fit 4 of these. But because you're encoding the more common letters with fewer bits, you can pack more into that. So you see the 4-bit long tokens are the vowels, essentially. Okay, so I don't know if anyone knows what this is. I didn't know what it was until I looked it up. It's an otterine. And the reason I have a picture of an otterine here is because otterine is the only 7-letter English word that fits into one token. So it's the only 7-letter English anagram of R-T-O-E-A-N and I. So that's the only one. But of course, you can invent other words that fit in. So you could have like tear, or I mean, you don't have to use English words in Colorforth. But so the concept that you can potentially pack a 7-letter word into one Colorforth token is kind of misleading, because it doesn't really help that much unless you want to have the word otterine in there. So this is what happens if you type otterine and also empty into the Colorforth editor, which is what you're seeing here. So in order to see what it actually has put into its source file or source block, you can do a dump. You can do 64 block dump. So this produces a hex dump of block 64. So just go back here. If you look in the top right-hand corner here, 64 indicates you're on block 64. Each block is 1024 bytes of, or more correctly, it's 256 32-bit tokens. It's a better way of putting it. So what you see in this screen, this first 32-bit word is the hex value, and this next one is the address of where it lives. So 64, block 64 starts at address 2 and then 4 zeros. That's because there's a system underlying it at 1 and 4 zeros. So anyway, that's where it is in the system. So you can see here that there's a long sequence. 3251764 is the Shannon-Fano encoded string, otterine, just for example. But you can see here that it's quite useful because empty, for example, is a fourth word. And this is what empty fits into. So that fits into one token as well. If a word is longer, then you can use an extension token. So these top three are all a token color of 9, which means white, lowercase. Then you'll see that after, I'm sorry if I keep pausing, I lose my cursor, it just vanishes. Anyway, this one here has a color of 0, which means it's an extension token. And this means that it's gone again. Curious. Okay, so I'm trying to present on the screen Colorforth, and that's a long word. An extension token, because every token, when it's displayed, ends with a null, the 4-bit null, saying this is the end. Or even if it doesn't, if it runs to the end, if there's no extension, it produces a space. So there's no spaces in the source block. There aren't any. So what you do is, if you want a longer word that won't fit in, you've got color and an F here, which is this hex number here, and that's a type 9, meaning white lowercase. And then I want to carry on, so it's a 0. So this carries on with auth here, which is encoded by these. And then, because the next one is not an extension, but it's a 9, then it leaves a space. That makes sense. So anyway, it carries on, and this is the way hexadecimal bit patterns, want to think of it that way, are outputted as characters that look like they could be ASCII, like every other character set in the world. These things here, the orange ones, just in case you're wondering what all these squiggles mean, are the same 4 bytes here, expressed as if they were ASCII. So this is hex 32, 51, I presume, is a V. I haven't checked all these out, but anyway, this is my dump program, which prints out what the source is in both ASCII in the orange and in Colorforth, colorful tokens, depending, just to say that the E color is blue. So this is a CR, and that's a blue token. And this is a purple, magenta, that's a C, etc. And a 4 is, that isn't anything. That's because the following cell is a the value of the variable. Okay, move on. So this is how you see it. Just type 64 block dump and it's there. So this is going into this in a little bit more detail. You can see that each 32-bit token is 28 bits of the string packed in. It's a bit like a zip file. You know, you got a file and you can compact it if you know how to do it. And this is just a very simple, elegant way of packing realistically 6 character names into one token. I still think it's useful because it means that you can have a dictionary which only has 32-bit tokens. So it's very quick to scan through a list of 32-bit values. But it does mean that you're only realistically going to get uniqueness over the first 6 characters. I'm thinking about changing that so it detects an extension token in the next cell, but it will make things run less quickly. Okay, so these, this is pictures of what I was just talking about here, that the color of the token is the rightmost number there, and that's 9 is lowercase text. Okay, so this is the idea that I had on April the 20th, 2022, after a search of lasting many years, I think, not full time, obviously, but it's just the thing. How can I express characters? Let me just flip back here. If you look at the list here, you've only got 48 characters here. You've got 8 4-bit, 8 5-bits, and 32 7-bits. And you will notice that in that list, there's not, you obviously can't fit a full ASCII set. So there's no greater than, less than, there's no tick. Oh, sorry, there's a tick. I've never used a tick. I'm not even sure it exists on the keyboard. Oh, that's an interesting one. Okay. But anyway, you haven't got a full set. So what do we do? Because Forth, the ANT's Forth at least, what do you want to do if you want to create a word that's called swap byte? This little symbol here, which is, I think, I don't know if it's an ANT's word, but it's certainly popular in most systems. It means it swaps the 2 bytes in a 16-bit value. And so I had this idea, which was so simple. I can't believe it when I thought it up, because I thought of all sorts of complicated things. Of I define a new color that sets up a color mode, or I have a token text type ASCII. But all the ideas I'd come up with meant that I needed an extra color, and I needed it would restrict these characters only to that color of token. So it said, if it's a color whatever, then it isn't a Colorforth token at all. It's an ASCII token. So I thought that's no good, because I can't have a word name, for example. I could have one sort of text that has that color. I do have a spare color. It's used as gray color in the ArrayForth system. Anyway, the idea is so simple. If you create a Colorforth token in a conventional way, and you start it with a 0, a null string, it's a 4-bit token, so it's just that null there. The Colorforth display code will see that and say, oh, that's the end of the word. I won't do anything. So it takes no action whatsoever. So what I do is I detect it, and I say, okay, if the first 4-bit value of my token is a null, all zeros, then I will take the next 3 characters as ASCII or UTF-8, whatever you want. You're into the 8-bit world of normal characters. And I published that on AlexForth, and there's a link to it, but I wouldn't bother trying to write that all down because I'll paste the links in afterwards in the chat. Or you can access these things via my Colorforth page. Okay, so this is some actual Colorforth. There's an actual Colorforth block, and it's presenting greater than, less than, and equals, and which are not part of the Colorforth character set. So they don't exist. It's not on the keyboard in any form. You could add a keyboard, you could change the encoding to include them, but this is much easier. So you can see here, this is the code here, that you can see the two lines that have got the ASCII in, or they both begin with a 0. Well, that was clever. I moved to the next screen by clicking my mouse. I didn't mean to do that. Right, but there you go. So that's the ASCII text. So the first 4 bits of the Shannon-Fano encoded string is a null. So it says, okay, I'll treat that as ASCII. And for those that know ASCII by heart, it's a 3E is a greater than sign, and so on. Okay, I just wanted to go back to Chuck Moore's comment here, because I think this is so cool, where he kind of reinforces my own attitude that I'm involved in Colorforth because it's fun and I like to do it. And you do find occasionally people question why. I'm going to move on and try and explain why in a second. But I like the fact that Chuck has been there first, and he's worked out that we don't have to ask the world to allow us to do this. Just because everyone else uses ASCII, we don't have to do it. So, okay, so what this is, I'm now going to try and explain what this is about. So this is something I took again from my from a presentation I did for the Kustenforth, is it called, in Hamburg. And it's what I call shortening the conceptual gap. The idea here is you have a human being represented by Lisa on the right, and you have a computer represented by Lisa on the left, the old Apple Lisa. So I thought this was a good thing. So the idea is to connect them as efficiently as we can. So to make that gap as short as possible. And in between this gap here, this little otterine, which represents the compacted Shannon-Fano coded string, which is, it sits in the middle. It sits between the human being. The human being knows what it is because they look at an editor, and the editor displays it in a text form that the human being can read. And the compiler reads it because it reads the 32-bit value, which it can read in a single fetch on a 32-bit system, which it can scan using these the opcodes optimized for doing this kind of thing. So the whole system is very quick and elegant. So the concept of the 32-bit token means that there's a very simple connection between the person and the output on an editor and the computer that has to read it and say, okay, what does this mean? Just going back quickly to the hex here, when it looks at the token color, this one here, it's a simple, okay, the token color and the bottom 4 bits, and say, what is it? Well, it's a 9. Okay, I know what to do with a 9. It's a case of 9, which means do this, output it, set the color to white, output it. If it's a 0, it says don't change the color and output it. And actually, it says don't change the color, step back a space and undo the space that the last token put down. And that's why you can see the auth there is to the left by one space, because I use the same primitive to output it in the dump program as I do to output it in the editor. So for the compiler, for the system, the computer, it's extremely easy. It's very quick. It doesn't have to do anything. This is Chuck's pre-parsed source. I want to call it that. This is a neat way of putting it. So it's very, very easy for the computer to analyze, to process, and it's very easy for the editor to present it in any particular way. that we feel like doing. So you can see here, for example, that the word test is in red. Okay, so I just wanted to emphasize again that I'm going to carry on doing this because it's fun and I don't care what the rest of the world thinks. But I hope you can see there might be a point to it in the end, but I don't know what it is yet. Okay, so back to this. And that's it. Questions or Fragen?
Amazing, amazing.
Thank you.
Was there a point to actually using the Shannon Fado encoding versus plain old ASCII besides saving space?
Yes, it does have the effect of saving space in the sense that you can pack realistically up to 6 characters. So you can have a word like empty, or you can have, there's quite a few fourth words that are quite short. And it means that you get 6 or even 7 unique characters. So obviously, if you have something like empty 1 and empty 2 and empty 3, they will be interpreted as the same thing in the current scheme. But it means that your entire system can just work with these fixed size 32-bit chunks. So there's no string length involved. There's no working out, is it this string? It has the same length and going through all n characters. It's imperfect because you only have 6 characters that have that are used internally, essentially. But it means that everything becomes much simpler. You can do things that do not produce an overhead when you run it. And it also makes the program a lot smaller. Not a lot, not a great deal smaller, because you've added 4 bits for each one for the color. But yes, there's very much a point to it. It simplifies everything else.
Do you get a lot of performance gains also with by doing this?
Compilation speed is basically as high as I could possibly think it could ever be, because the x86 architecture has these instructions, what are they, LDAX and things, and they have rep instructions. So the dictionary search, maybe this is time to pop over to the editor. I wonder if I can do that here. I don't want to stop sharing. I want to get back into my screen here and then leave this one here and then come back to here. And amazing, I had all these things open and of course I've closed them. Somewhere here there should be this one. Okay, so if I find, for example, what's it called? Yeah, if I look for empty, that's probably a quick one to find. There'll be a few others on the way, text and things. So that was the code for empty, and then somewhere here. Here we go. Right. So the this is the Colorforth dictionary, and this is the fourth names in ROM. And so these are the Shannon Fano coded parts of it. There's always a 0 here because it ends out the bottom bit, so it doesn't mean anything else. So if I now search for one of these things, the next table you'll find is a table which has a one-to-one correspondence of the code. So in every other fourth system, you've usually got kind of a name somewhere and then a pointer to the code that it has to run. So the action of compiling is that it searches through this list of 32-bit values. Say, is this the 32-bit value that I've got? And that is extremely quick. And if you think about it, there can be, you could have any other sort of hash. You can, I think, Bernd Peisen or maybe somebody else, they came up with a hash that managed to hash all English words very reliably. So you could, but I think that's 32 bits. So you could create any other sort of hash. It doesn't have to be a code, a bit sequence that can be expressed as a string. It doesn't have to be, but if it is, then you have a simplification that you don't have to look up what does this hash mean in a table. You simply unpack it. The inefficiency there is the unpacking. It's obviously more complicated to display something that's compacted. You have to uncompact it. But that happens at the time that the person looks at it, not at the time when the computer compiles it. And the person doesn't know or care that it's being unpacked. You can't tell. It's so quick that the human being wouldn't care. So this is the internal point of it, if you like. It means that you only have to concentrate on a fixed bit size, a 32-bit entity. And for all actions of what the compiler has to do with it, you just have to focus on the bottom 4 bits. And for everything that the human being wants to see, it's on the other bits.
Cross-compiler.
Sorry, I'm hearing somebody saying something, but I can't quite make it out. I mean, how am I doing for time? I didn't time myself when I started.
Howard, the meeting is really over, so we have time if you want to say, talk a bit more, because there are no more participants. I asked Chang Luke to to make the presentation. Are you there, Chang Luke?
Yes, I'm here. Can you hear me?
Yeah,
now,
we can,
yes,
we can hear you.
We can.
Okay.
We can.
Okay.
So now I can. I'll share my screen with you. Okay.
Perfect. Sure.
First, I want to introduce the assembler. This assembler can be designed. Can be generated automatically by assembler. But first, you have to design your own assembler. Once you understand how to design a single instruction like this,
Chang, we cannot see your screen. If you can share your screen.
Oh, yes. See, can you?
No, yes, okay, perfect.
Okay, now, let's see. It's only a page of screen, right? Once you understand the instruction format for this one, you'll be able to design all the other instructions as well. This is the one this picture is the one I take from the website here. You'll find that the OP code structure of each individual instructions. From here, you can see this one is logical shift left, and it has 5 bits of OP code with constant. So we say this is 5C, and also a number with 5 numbers bit, and 3 RM bit, 3 RD. So we can say this format, this instruction format is 5C, 5 number, and 3 RM or 3M briefly, and 3 RD. Okay, all the other instruction format can be expressed like this. Now let's switch back to our main program. Here, this is the format of the one I showed. This is 5C5. Anyway, we can say this is a defining word. It is to define the assembler of this instruction. And I prefer to use algebraic assembler or style of notation. So we have 2 choices. You can use original mnemonic or use the algebraic assembler or assembly language. And also I had more than 5 or even 10 of the expression that can be used in my assembly language, including force virtual machine and virtual and macro instruction, and also the postfix notation and infix notation. So it's really very different from the traditional one. From here, we can load it to the main program, the main system. Here I use Win32Forth. I would say nobody else in the world use this kind of force again, Win32Forth, the old version. But actually, I can execute it under Win 10 or Win 7, 64-bit system. So it's no problem. But you have to copy the main program from the one that generated by XP book, Windows XP or former version. But mine is okay to run in under Win 10, 64-bit system. And it works very well. And I use it for all the design of the cross compiler system, including the assembler, disassembler, and the cross compiler and decompiler. So now we are going to pass it to, here. Now we can execute it by, say, this is a very basic, assembler that can use. We use postfix notation. We say 1, 2, 3. Logic shift left. Okay. Now it's okay. But where are we now? Oh, this is in Win32Forth system. So we can still execute it. So here again. Oh, it's increment by 2, right? And we can see the object code that is generated here. We can say fetch and print it. So it's D1. So the same for the other, we can do it like this. This is the algebraic assembler. Now we can use it. The same number entered first. And now our address advanced by 2. So our new is here. Okay. Yeah, it's still the same. Or we can list all the command or the code that generated here. So we have 2 instructions. The first one is generated by this one. The second one is by this. Okay. But this is the first thing you have to know, how to design an assembler. It's quite easy. Once you understand how to fill each bit region with the register. So 0, 2 is here, and 5, 3 is here, M is here. And the number is from A. We use hexadecimal system. So now we put all these together to get 16-bit of object code. And then in comma it to here. Okay, this is the basic. Now I'm going to switch to more advanced one. You'll see. Oh no. I'll say this one. Okay. This one is the same as the former one, but we add here, this line of program, and the other one here. These two lines are added to generate the disassembler when it is assembled the instruction. When we assemble this instruction, it will generate the disassembler like this one automatically without having to redesign the assembler. I would say this is the only one disassembler that can be designed or generated directly by assembler, I would say. So once you understand how to use it and very simple, like this, then you will be able to design your own cross compiler. Once this one is executed, and then disassemble result, the result will be here. Okay, so now let's try to use this one as the source code. This one has been used in RISC-V assembler and disassembler design. RISC-V. I use this for all kinds of microcontroller like ESP32 or ESP8266, even Parallax, even MSP, both 30 and 8051, and also Cortex M0, M3, and 8065, 8051. Now, I'm going to load the program. Oh, it seems that this one, okay. FC1. Actually, I put all this in the GitHub, so you can see my program here. Now we can press any key. Okay, so now I'm going to load the source code of this one. This is the source code. We here only have 4 instructions here. So I'll just load one first, just to show you how one assembler can be designed by this. Oh, what? Oh, I didn't put the source code here. This is the source code of the defining word. We can say this one is defining word. So we can now load it first. Defining word has to be loaded first. And then we can use it as the defining word to develop the assembler of each individual instruction. Here. See? This one generate the one like this. And and here it has original mnemonic here. And the other one, we can say original mnemonic of. I would say everyone can understand this very easily. See, the same like this one, but it has no original mnemonic. So we can choose between the original mnemonic and the algebraic assembler. And then from this, we have to load it to the system to use. So now I can load it. Okay, now it's been loaded. And the second one is also okay. But actually I put all this in a file, not just by one by one. Okay. So we have 2 assembler being loaded. Now we can use it. Disassembler, this is disassembler, and the assembler is, yeah, this is the assembler. Okay, so we can use this the same like say 1, 2, 3. Okay, before we execute this, we have to know where we are now. We use hex here, prime, instead of here, because prime means the target image. Okay, so we have here, we can disassemble it, and we can see what we here. Here is 0, but we can say 32-bit fetch. We can read it, right? The same like it was which we have shown before, D1. And the same, we now can execute the same like this. The second one here. So the same, 2, we fetch it. See, the same. So it means that the 2 instruction has been, successfully compiled and assembled. So we have put all this all this together. You see, the first is this one, right? Okay. The rest of this can be done the same like this. So we can now load this for this file, DISXE2, to the system to verify. Include DIS. Yeah, it's okay. But the first 2 has been redesigned, so it's okay. So anyway, this is a very basic assembler, disassembler design. Once we have assembler been designed, then the disassembler can be generated automatically without having to redesign it. It's a big engineering effort to do if you want to design your own disassembler. But the assembler like this one is very easy to design because of it's just you have just to fill it with the number. It's just the same like you hand manually, coded it, code the OP code. So it has no anything like a swap over or rotate over all those things. So it's very easy to design this kind of assembler. And I have used this to design all kinds of assembler, disassembler, and now you can see here. We have include file here. Oh, we have RISC file RV32 C type of instruction set. So you'll see the original instruction like this, original assembler. See? It's only about 600 lines of instruction, but it's only C, means 16-bit of instruction set. But for other 32-bit, we have other files to use. And this is the STM103 eForth that I developed. I ported from Dr. Tim's eForth, and I added a Proforth and even Musqueforth to one chip. So I put all the program and the hex file in the GitHub, so you can burn this into your blue chip. Then you can run 3 systems very easily. Okay, and when you see the compile system, the close compile system I designed to develop the whole program. When you see this one, you'll see it use macro to express, all the assembly language program. But of course, not all the program has to be expressed like this. Anyway, you can see like this. This is tube, right? It's the macro of tube. And R6 equal to 556, RB, R0. So from here, you can see very easily. But the traditional one, I would say, will confuse me because of the use of...
This is okay. Thank you for presenting, Chang Luke. I see we are very nice done. If you can share the file on GitHub with us, we publish this on the group.
Okay, thank you. Okay.
Thank you. Okay, guys, the meeting is over. We had a very nice meeting, and it lasted for over 4 hours. We started with an early fourth cafe, very long talk and very interesting for me. So I thank you, every participant, very much. We are stopping the recording now.